Hello, student. Welcome to this chapter, electricity and magnetism. Yes, this is the session 16, and here we are going to study the magnetic field on the axis of a solenoid. So, what are the learning objectives in this class? Now, we have to establish a relationship showing how the magnetic field of a solenoid varies with the distance and current using the Bert-Savart's law. And to calculate the magnetic field of a solenoid from its current, radius, and the number of turns, and to understand how the solenoid creates a magnetic field. These are the learning objectives. And at the end of this session, we should we are going to derive the expression for the magnetic field due to a current carrying solenoid, and knowing how a current carrying solenoid acts as a bar magnet, and how its polarity will be, that also we are going to see, and the factors on which the strength of the magnetic field produced by the current carrying solenoid depends, that also we are going to see it. And prerequisites, and here we should know the equation of the magnetic flux density at a point produced by a current carrying loop. Based on this result, this present derivation depends. So we should know first what is the expression for the magnetic field produced by an coil carrying current. And in this diagram you are looking here, a current carrying loop is there, like a single copper loop, and some current I is flowing through this loop, and this is the radius of this loop, capital R, and this is the axis of the this current carrying loop, single loop. And here we are taking an element of this loop, and using the Bert-Savart's law, I am going to calculate what is the magnetic field at this point. It's very simple. Then uh, to calculate the magnetic field at this point P due to the whole coil or loop, we have to integrate the equation, and we are going to get the result. So these are the results. This is at the center of the loop, and this is the expression for the magnetic field at any point on the axis of the coil. So this is axis of the coil. Anywhere you can check this point P, and we can get the magnetic field at that point using this relation. So this relation for magnetic field induction is mu naught I divided by 4 pi into 2 pi capital R square divided by x square plus R square whole raised to 3 by 2. And here x is the distance between the point P and the center of the coil, and this capital R is the radius of the coil. So this result is very, very important. And we are also going to see what is the meaning of a solenoid. A solenoid, this is the single coil, and suppose if this coil is having very large number of turns, so that its length become very, very greater than its radius, then that kind of coil is called as a solenoid. It's very simple. So Biot-Savart's law is also I am going to explain because here just now I told the result is used, and here, yeah, this is in the picture you are looking uh, a conductor, any conductor carrying some current I. Here I is there, and on this conductor I am going to take a small element of length dl, and this is the point where the magnetic the expression for magnetic induction is needed, and this point is at a distance r from this element, and this is the direction of the length of that element, and this is radius vector. So between these two some angle is there, that angle is very very important. And you say here this expression for this small magnetic field induction produced at this given point is given by dv is equal to mu naught I dl into ir divided by 4 pi r square. Okay, and in this expression mu naught is the absolute permittivity of the free space. That means this conductor is kept in the free space, therefore the permittivity of the free space is required. And here also in this expression, due to a single current coil, here also that mu term comes because this coil is kept in the free space. So these are the prerequisites, or the knowledge we should have before going to derive an expression for the magnetic field due to a solenoid. So this is the solenoid. I have shown good pictures for this solenoid. Simply, this is a copper coil. It's a copper coil. When the length of the coil becomes very, very large as compared to its radius, that kind of coil is called as a solenoid. So this is called as a solenoid. Therefore, a solenoid is basically a copper coil which is having very large number of turns, and length of the coil is very large as compared to its radius. Such a copper coil is called as a solenoid. So a solenoid is the same thing is written here. You can go through it. So once the current is flowing through this solenoid acts as a magnet, a bar magnet. So the magnetic lines of force, which are their direction is shown in this figure. In this figure, so you can see here the magnetic lines of force. They are passing like this, and circle the coil and comes inside like this. So in this way, as you know, the magnetic lines of force are they are always closed ones. So therefore they are moving like this. So at this end of the solenoid, the magnetic lines of force are entering into the coil, and here they are going out of the coil. So therefore this end of the coil acts as a south pole, and this end of the coil or the solenoid acts as a north pole. So therefore whenever some current is flowing through the solenoid acts as a bar magnet. And now I am going to derive an expression for the magnetic field produced on the axis of a solenoid. So this is the diagram of the cross-sectional view of the solenoid. You can see these are the coils. Okay. So this is the axis of the solenoid. This is the axis of the solenoid. So inside the solenoid, on the axis of the solenoid, we have taken a point P here. So this is the point P, and this point P, and On the solenoid, here we have taken a small element of the solenoid, which may have some few turns, and its length is dx. And this is the AB is the part of the solenoid which is at a distance x from this point P. And so this is the R2 is the line connecting this point P and the right end of the solenoid, and that makes an angle theta 2 with respect to the axis of the coil. And R1 is another line which connects the left end of the coil, and that makes an angle theta 1 with respect to axis of the coil. And this R is another line which connects this element to the point P, and that makes an angle theta with the axis of the solenoid. And here this I is the current flowing through the solenoid, and this capital N represents the number of turns present in the coil, and this A is the radius of the coil. And here also capital L is there. Capital L means it is the length of the total length of the coil. So these are the things present in this diagram. And now consider a long air solenoid. Air solenoid means we have kept nothing inside the solenoid. Air is there. So it is called as a air solenoid. Sometimes this copper winding is done over a soft core material to increase the magnetic induction. At that time, the name will be different. So air solenoid means inside the solenoid nothing is there, air is there. So having closely packed circular coils, let capital L be the length of the solenoid and capital N be the total number of turns and small n be the number of turns per unit length of the solenoid carrying a current I of radius A. Consider a small portion AB of the solenoid having length dx at a distance x from P. As shown in the diagram, here we have taken a small element of this solenoid which is at a distance x perpendicular axis. Perpendicular distance of this element from this point is capital X. So number of turns in the length AB means in the element is n into dx. So this is equal to capital N divided by L. So this capital N is the total number of turns present in the coil, and when that total number of turns present in the coil is divided by the total length of the coil, so that gives something like turn density or the number of turns per unit length. That is denoted by the small n, and that is multiplied by dx. Therefore, this gives the total number of turns present in the element AB. The magnetic flux density at a point P produced by the current element which acts as a coil is given by. We'll go to next. So this is the this is the magnetic field induction at point P produced by that element. So this is written directly because we are making use of the Bayard-Savart's law here. So it is directly the case of the Bayard-Savart's law, and using this Bayard-Savart's law, no, and it is also the case of a coil, a single coil carrying the current. So using those two results, we are writing this equation one directly. It is a direct one, and so all things are there. A square divided by x square plus a square whole raised to 3 by 2 into dx. So all these things I have explained. The direction of GB at point P is along the axis of the solenoid to the right if the current is flowing out of the plane of the paper, and to the left if the current is flowing into the plane of the paper. This is not just uh, done with the help of Maxwell's thumb rule. We can make use of the Maxwell's thumb rule, and that gives the direction of current and the magnetic field. It's very simple. Then from the figure, cot theta is equal to, it is actually reciprocal of tan theta. So therefore, tan theta means it is opposite side divided by adjacent side, but cot theta is adjacent side divided by the opposite side. Therefore, OP divided by OA, this is equal to x by a from figure. So here, uh, in the figure, it is OP is x, OA is a radius of the coil. So these are the things present here, and therefore x is equal to a cot theta from this equation. Differentiate this equation, it becomes dx is equal to minus a cosec square theta d theta, because the differentiation of cot theta is cosec square theta. So simply the trigonometric formula is used here. Then substituting the value of x and dx in equation 1, this is the equation 1, we will get like this. So the equation becomes like this, and substitute those two values and multiply this thing to here. It becomes minus a cube cosec square theta d theta divided by that thing is there in the denominator. And in the denominator, this a square is constant, common. Take it out, and remaining is cot square theta plus 1. And this cot square theta plus 1 by trigonometry is cosec cube theta. So that is written here. Sorry, that is written here. And then what happens? This cosec square theta and cosec cube theta get cancelled, and one sine theta, one cosec theta remains in the denominator, and that is the reciprocal of cosec theta is a sine theta. So that is written here. Remaining things are there. That is minus mu naught by 2 Ni by L into sine theta into d theta. So in this way, this equation is simplified. So this is the magnetic field induction at the given point P due to the element only. And now the magnetic field at P can be obtained by integrating the above equation between the limits theta 1 and theta 2. That means actually we need the magnetic field due to the whole solenoid. So we have to integrate this equation 2 between the limits theta 1 and theta 2, because these are the two angles made by the lines connecting the point and the two ends of the coil. So if you integrate equation 2, we will get the total magnetic field produced by at point P due to the pole solenoid. So this is the integration. B is equal to theta 1 into theta 2 into dB and so to dB, and go on simplifying. You see, it is simplified, where you are coming here, and it is written, and the integration of cos sin theta is minus cos theta, and integration limits are theta 1 to theta 2, and put the upper and lower integration and simplify, and the equation comes like this: mu naught by 2 Ni upon L into cot theta minus cos theta 2 minus cos theta 1, after substituting the integration limits. And this equation is slightly modified, because here capital N by L is there, that is the number of lines per unit length, so that is also included here. It is mu naught Ni upon 2 into cos theta 2 minus cos theta 1. So in this way the expression is simplified. The direction of B is parallel to the axis of the solenoid, so it is always the direction of the B is always parallel to the axis of the solenoid, and whether the B is towards right or left depends upon the direction of the current. Very simple. Next here, special cases comes. So case 1 is there, solenoid is of infinite length, and the point chosen is at the middle of the solenoid. At that time, what happens? Theta 1 becomes 180 degree and theta 2 becomes 0, because I will show you how this happens. You can look at this diagram. When the length of the coil goes on increases, this angle theta 2, it becomes decrease, smaller and smaller, and last it becomes 0. And this angle, which is made by the line R1, that is theta 1, it becomes greater, and lastly it reaches a 180 degree. So when the when the solenoid is of infinite length, we can take approximately theta 1 is equal to 180 degree or 5 degree, and theta 2 is equal to 0 degree. So therefore, then the above equation becomes, that means the equation 3 becomes like this, and here cos 0 is also 1, uh, and but cos of 5 degree means 180 degree, that is minus 1, so minus minus plus, so the total it gives 2, that 2 and this 2 get cancelled, so remaining is mu naught n I. So that is the expression. Next, another case, solenoid is of infinite length and point is at the end of the solenoid. So here we are shifting the point to any one end of the solenoid. At that time, what happens? Theta 1 equals 90 degree, theta 1 becomes equal, suppose here the point is shifted to the left end, so here theta 1 becomes 90 degree and theta 2 becomes equal to 0. That is the case, and substitute these theta values in the magnetic field induction equations like this, and here cos 0 is 1, but cos of 90 is 0, so the second term goes to 0, and remaining is mu naught n I by 2. So this is the second case. Another case is there, that is the case 3, magnetic field at the center of the solenoid. So when the point is exactly at the middle of the solenoid, cos theta 1 becomes like this, L upon 2 divided by A into root of A square plus L square by 4 raised to half square, because cos theta means it is adjacent side divided by hypotenuse. So this is adjacent side divided by hypotenuse. Adjacent side means it is half of the solenoid, so it is L by 2, and this is the hypotenuse. Similarly, the expression will be same because the point is exactly at the middle. And substituting the values of cos theta 1 and cos theta 2 in the equation, this equation, and we have to simplify. Here we have substituted and we have simplified, and lastly it becomes like this. So therefore B is equal to mu naught n I divided by 4 A square plus L square raised to half gives the magnetic field at the center of the solenoid when the solenoid is of infinite length. So if you placed, as I told here, the solenoid initially is an is an air core solenoid. Air is there. Suppose if iron core is there inside the solenoid, then that mu value changes. So that is mu r. Then we have to take mu r, relative permeability. Then you'll go for the MCQs. The magnetic field inside a long straight solenoid carrying current is is the same at all points. That means when the solenoid is having a sufficiently long length, at that time what happens? The magnetic field slightly varies only at the ends, but well inside the solenoid it is uniform. So therefore, the magnetic field inside a long straight solenoid carrying current is same. Answer is the same. It will be same at all points. Second question: whose magnetic field is like a field of a bar magnet? As I told, it is a current carrying solenoid. And here, this is a small problem. A 50 centimeter long solenoid has a radius of 1 centimeter and is made up of 500 turns. If it carries a current of 5 ampere, then the magnitude of magnetic field inside the solenoid, this can be calculated using the formula. So this is another formula. This also is just a workout. And if the current flowing through each turn of a solenoid is in the same direction, the magnetic field produced by n turns will be multiplied with the magnetic field due to each turn. So this is very simple because this solenoid is an extended part of a single coil. When the coils are placed side by side, you will get a solenoids. Therefore, the magnetic field produced by each coil is go on adding. So that is why just you multiply the magnetic field produced by one coil with the number of coils, you will get the total magnetic field. Okay, and this is the summary, and you derived an expression for the magnetic field uh, intensity on the axis of the solenoid, and derive the expression for B at the middle. All the cases we have seen and discussed the effect of current and the number of turns on the magnetic field intensity due to the carrying current. So this one, effect of current and number of turns on the magnetic field intensity is directly proportional to each other. That means higher the number of turns, higher will be the magnetic field produced. And also current, if higher is the current, higher will be the magnetic field produced. So that is the effect of current and number of turns on the magnetic field. Okay, this is the summary, and these are the reference books available in our library, and go to the library and read again, and you will understand the subject. Thank you for listening. Thank you, one and all.